Alright, we're going to talk about a new statistical distribution today, notably the normal distribution. Essentially, it's been noticed throughout history that a lot of data behaves a certain way. So it originated with measurements in astronomy where people were off by a certain amount, and they found that if you stacked it all up, all the different people measuring the same thing, that you ended up with a shape kind of like this. This is something you see all over the place. You'll see it in geography a lot with the height distribution of people, the distribution of the ages in a population, and all this kind of stuff. And essentially what it was noticed is that it had this shape of a bell curve. So a couple of mathematicians tried really hard to figure out how can we turn this into something concrete and mathematical. It was a combination of different efforts. Gauss, I think, in the end was the one to really figure it out. Essentially, they wanted to create the perfect bell curve so that we could then apply it to certain models and make predictions. So in the end, the normal distribution is just going to be modeling something as a perfect bell curve. And it's going to look something along the lines of this. And we're just going to be able to make it thicker, thinner, taller, lower, move it around depending on what the values we're looking at are. And what we're going to actually do is we're going to base it, so the middle value is going to be the mean of my data set. We're going to call the mean mu, just because, Greek letters. And the other thing we're going to do is we're going to determine its thickness as the point of inflection, so right where it goes from being really decreasing to maybe flattening out a little bit. We're actually going to measure that as one standard deviation. So we're going to revisit some of the stuff we saw at the beginning of statistics to do this. And so we're never actually going to use a formula for this because, again, our calculator kind of does it for us. But if anyone is interested, there is a specific formula for this, which I think Gauss came up with, which is something horribly scary looking like this. And don't worry about it. And because the probability or the proportion of the whole thing is going to be the area underneath it, just to make matters even weirder, we are going to actually be looking at the integral of this. But do not worry, we're never going to see this. We are going to be using our calculators, essentially. So the question is going to set out that a certain set of data can be modeled using the normal distribution, and therefore we're going to pretend that it works this way. Now, there are going to be a couple of things that we have to keep track of. So first of all, because the mean and the standard deviation are used to essentially measure the thickness and the height and the location of it all, we are going to refer to x. So for example, the probability variable can be modeled using the normal distribution of mean mu, or whatever it will actually be, and standard deviation sigma. But what we're actually going to do, just to make things even more complicated, is this is actually going to be the variance. So we're going to write that as sigma squared. Now we need to define this such that mu is the population mean, and sigma is the standard deviation, and therefore sigma squared is the variance. Now, what we're also going to do in this perfect bell curve scenario is we are going to model the curve as symmetric. So this has implications. If the curve is symmetric, what that means is that the mean is perfectly in the middle. There's as much on the right-hand side as on the left-hand side. It's also the highest point on the curve. So what is quite neat about this is that in the case of the normal distribution, the mean, which we're using, because it's also smack in the middle of the data, is actually the same as the median. And because it's the highest point, it's also the same as the mode. So on the off chance you get a question about that, we are mostly going to be using mean and standard deviation, but on the off chance they ask you about the median, we can actually use the symmetry of it to make comments about that. It is bell-shaped. However, what is maybe not so obvious is that it is actually infinite. In the same way as we've seen some graphs get closer and closer and closer and closer to the axis without ever reaching it, in order to kind of model all possibilities, we just set it out as having asymptotes on either end. Now, this isn't particularly realistic, but our way of making up for it is after a certain amount of detail, it becomes so small that it is statistically negligible, and we can kind of put an end to it right there. So the other thing is the total area under the curve is equal to 1. Now this might seem a bit strange because you may never have seen infinitely long graphs that have a finite area underneath them. It exists. In second year A-level we look at infinite series that actually converge to finite numbers, and the same thing actually happens with curves. And it turns out, even though this goes infinitely this way and infinitely this way, getting closer and closer and closer to the curve without ever touching it, that the total area, including both infinities, is 1. And this needs to be the case because when I'm dealing with probability, or when I'm dealing with proportion, the full amount needs to add up to 1. And finally, the thickness, the width that we talked about, is that it has points of inflection at mu plus or minus sigma, so that we get this kind of thickness here determined by it. Now, points of inflection, as I explained before, is kind of where the direction changes behavior. We talk about points of inflection in a little bit more detail in year 2 of pure mathematics. You don't need to worry too much about it. It's just occasionally they might refer to it, and you just need to know that that is 1 standard deviation away from the mean. So, what's interesting about this now is we can actually model things using this, and we have a calculator that does most of the work for us. So I am going to just do a couple of basic questions using the calculator function just to kind of show us how to answer questions involving the normal distribution. So here's a question that we can look at. It doesn't involve any words, but here I've just cut to the chase. I've given you a distribution. We are going to do stuff with it. So this could be anchored in an actual word problem where it says this data can be modeled by the normal distribution. It has a mean 35. It has standard deviation 3. Technically, they could also say variance 9. So just look out for it. Technically, you could also be given x modeled by the normal distribution 35, 9. And it's up to you to figure out that what that actually corresponds to is that sigma is equal to 3. So if there's no squared symbol here, you do have to square root it to find the standard deviation in the problem. So we're just going to use this and use the calculator to figure things out. There are a couple of tricks that we can kind of use that we have up our sleeves and stuff to figure this out, but it is mostly straightforward. Just to show you how to use the calculator, we want to go to the menu, and in the same way as we did with the binomial distribution, we are actually going to go to distribution. So you could either hit 7 right away or hit equals at this stage. And here we have normal PD, normal CD, and we saw that we have a lot of binomial stuff down there. We are never going to use normal PD because that involves the height of the curve, which is the probability density, which isn't really talked about at A-level maths. But we're going to use the cumulative distribution, which will talk about the area under the curve. So we're just going to hit 2 right there. And what we have is lower, upper, sigma, and then 1 down we have mu as well. And we're literally just going to fill this in. So for all of these, I can have sigma equals 3, mu equals 35. So if I write this down here, it should look like that. Now we're going to have to negotiate with the upper and lower. There will always be an upper and there will always be a lower. And this is where it might get a tiny bit confusing, because for part 1, for example, I'm looking at a normal distribution where my 35 is in the center and my points of inflection are at 38 and 32, and I'm wanting to figure out what the probability of getting less than 33 is. So if I actually write this down, what I'm looking at is all of this area there. And I have a nice point here, less than 33, which means that on my calculator I can write upper 33 so that it looks like this. But I have to write something for lower. And the problem is that this goes infinitely on forever, so I do not actually have one specific value I can type in for lower. What we do is we just take a ridiculously small number that is statistically negligible. So it has to be at least 5 standard deviations away from 30, but I'm not even going to worry about that. I'm just going to put a really small number like minus 100. Because there's no way that that is actually going to produce anything of use that small. So it should look something like this. So if I hit equals, we get a number. And that is literally it. So using the calculator, I can find that p of x less than 33 is equal to 0.25249258283, and it's always worth giving this to whatever degree of accuracy they ask for. It's nice to do 4 decimal places, although the minimum for the exam will most likely be 3 significant figures, so you can cap it off at 3 there if you want. And that's it. You just have to use some problem-solving understanding to figure out the problem, but in the same way for 2, I'm looking at p greater than or equal to 27. Now this is almost a little bit of a trap, because this right here, the greater than or equal to, it turns out this is just a trap that they might throw your way. This is exactly the same as p of x greater than 27, because all I'm dealing with is the area, so it doesn't actually matter whether that line is included or not. So if I use the same graph again, I'm looking at 27 plus. So it's somewhere here, quite low down, 27, and I want greater than. So I want the probability of getting more than 27. And again, we're going to use the calculator, we're going to keep the same sigma, same mu, and we're going to put the lower bound as being 27 and the upper bound as being something ridiculous. Let's say 100, let's say 1,000. It doesn't actually matter. Just type that in your calculator. Lower can be 27, upper can be 1,000 or something. Hit equals, and you get a number, and that is the answer, which to 3SF, or to, let's say, 4 decimal places, is that. And we can see that that is going to be most of the curve, so it makes sense. So now it turns out that this one right here is actually probably the easiest of them all, because it gives us 2 ends. So practically what I'm looking at is between 33.5 and 38.2, this area here. And that's perfect because our calculator is set up this way. So I'm literally just going to keep the same standard deviation, same mean, and just write 33.5 on lower, and then write 38.2 on upper, and we get 0.5484, correct to 4 decimal places. And then finally we get this weird one, which isn't as bad as it looks. So I want x less than 28 or x greater than 34. Again, we're going to look at it in this case. If it's less than 28, that means it's somewhere around here, 28. If it's more than 34, that means it's somewhere around there, 34. We're looking at that area there. Now, I could figure out that area and add them together, or if you're being a little bit problem-solving-y, you can just find this area and take it away from 1. That's 1 minus the probability of 28 to 34. And we can type that one quite easily into the calculator, 28 to 34. We get 0.35962601115. You can either write that all down, or very helpfully, what you are allowed to do with this is you can actually store that value to a letter and actually go back to menu, go to the normal one there, and write 1 minus alpha A, and it actually remembers it cross-platform from another section. So that our final answer is 0.6403739,885, or to 4dp that. So that's some basic calculations that we can do with the normal distribution. There's a whole lot of other things that we can do. We'll look at that in due time, but I hope that this was helpful.